Assalamualaikum and good morning or good afternoon or good evening. So in this lecture number 11, we'll be learning about properties of beam sections, part number 1. So in the previous lecture, you've learned the differences between a truss and a frame, and also you've learned how to use the method of virtual work for beams or for frames. And this lecture comes under CO number 4. So this lecture you'll find out what is a center of gravity, how do we find the center of gravity, and what is the centroid. So in the late 1800s, there was a shipping lane which a lot of ships at the time like to use this route to travel to London. But unfortunately, in this part here, with this red mark here, there's some rocks, very sharp and prominent rocks, which always cause a lot of ships to be wrecked. So what they tried to did was they put a lighthouse, and they put many lighthouses, not just one. And these two were some of the designs that were chosen. Now, which one do you think is more stable? This one or this one? Well, let's look at the shape. The one on the right is more of a triangular shape, while the one on the left is more rectangular. And why is a triangle more stable is because the center of gravity is lower than the rectangle. Now, what is a center of gravity? Usually people interchange center of mass, center of gravity, but actually they are both different. The center of mass is the point where the distribution of mass is equal in all directions, while the center of gravity is the point where the weight is equal in all directions. So center of gravity depends on weight, and weight is simply mass multiplied by the force of gravity. On Earth, there is a uniform gravitational field, so center of mass and center of gravity are basically the same things on Earth. But in space right here, they may not be the same thing. So let's find out how to calculate center of gravity, to find center of gravity in any object. So we have a rod here, and let's take a really small piece of the rod here. Now, this small piece of the rod has a small weight, dW, and the distance of dW from the end of the rod is x curvy bar, not x bar, x curvy bar, because x bar is for the centroid of the whole bar. Now, to find the weight of the whole bar is we simply integrate this small weight over the whole length of the bar. So that means we take small areas from here all the way to the end and just add them all up, and that's what integration does, and that gives us the total weight of the bar. Now, once we do that, let's take the sum of moments of W, about 1n here, so like this, to be the same as the sum of all moments from all the dWs, the small dWs of all sections. So basically, you just take all of these small dWs, you multiply by their x curvy bars, and that will be the same as this big W multiplied by x bar, which is the length of the centroid, the location of the centroid. And you do that here, x bar equals big W plus all of the summations of all of the small areas of dW. You work this out and you will get this equation, which is x bar is equal to the integral of the integral of x curvy bar times dW divided by the integral of dW. And remember, big W is the integral of dW here. That's why we get this one. If we have 2 dimensions as opposed to 1 dimension in the bar, we just replace x with y. We get this one here. If we have 3 dimensions, then we'll just add another one and put z. We can also replace dW, the weight, with G multiplied by the mass, or dm, because it's very small. So we have dm's here. We can also replace the mass with the density times volume, and we get this. So that leads us to the concept of the centroid. Centroid is the geometric center of the body, of any body. The centroid and center of gravity and center of mass are all equal if the material is uniform and homogeneous, which means it's made of the same material throughout the whole thing. If you have two different materials stuck together, then that's a different story. So sometimes centroids can be at a point that are not on the body, which is, for example, if you have a tube, for example, then the circular tube, the centroid of the circular tube will be in the middle of that tube, but the tube is hollow, so the centroid is not actually on the body. And in another case, you can have a C-channel section. The centroid will be somewhere around here. So that's another example of when the centroid is not actually on the body of the cross-section itself. So the centroid is the average position of all points on the body, and you get a point centroid here. And if you take a pen or pencil and balance this piece of paper right on the centroid, it will be perfectly balanced on the centroid. Coming back to that two-dimensional plate, we can replace dw with area to find the centroid. And when we do that, we find a much simpler and more straightforward equation that we can use to find the centroid. So this part here, the top part here, x curvy bar times small dA, which is x curvy bar times the small area here, this is actually qy, or it's actually q. Let's not talk about y and x for the moment. It's q. Q is the first moment of area, and I'll explain what moment of area is in the coming slide. But q basically gives us the distribution of an area, so this area, with respect to an axis. And because this is q sub y, this is the distribution of this area with respect to the y-axis. Okay, so let's try to understand what is a first moment of area. What does that word mean? When we talk about moment in physics here, the formula is force times distance. We also call this torque, and this is a demonstration of how moments are made. So you have a force here and a distance. This creates a moment. But in engineering mechanics, we have kind of a same concept going, where we have a distance as well here, but instead of a force, we have an area here. So an area and a distance from some axis is our moment of area. Now that we know the top part is q is the moment of area, the first moment of area, we look at the bottom here. Now this is just our total area of the blob, the summation of the small areas. You sum them all up together, you get the area of the big blob. Therefore, to find the centroid of any cross-section, you use this principle, which is the distance to the centroid is equal to the first moment of area divided by the total area. And we have these equations here, which is x bar equals qy over a. Notice that x and y are changed because x bar is here. Imagine this is x bar, it's going in this direction, right? X bar gives us this direction, which is when we multiply by a, we get the first moment of area with respect to which axis? The y-axis. So we have the y-axis here, and the distance between the y-axis and the blob is x. So that's why we use x bar for qy. and the same goes for y bar. Now let's look at an example, but this is a very theoretical example, not a very, there's no numbers in this example. We look at the first principles, the principles how to derive this centroid. Now let's write down the formula that we need to use. It's always advisable whenever you're solving problems to always write down the formula that you need to use, so that you can visually see which variables or unknowns that I need to find out. So in this case, let's find x bar first, which is the x coordinate of the centroid. So to find x bar, do we draw a horizontal or a vertical small area dA? It's an easy question, because to find the orientation of this area here, just follow the orientation of x bar. So if you want to find x bar, and then you write the area in this direction. So we want to find dA, sorry, we want to find, oh, okay. Let's find dA, and let's find in this direction, which is finding x bar. I think this is a bit of a mistake. This should be x bar. This one should be horizontally. Yeah. Okay, this one should be x bar as well. So apply this equation to find a first, because we don't know what a is. So a is the integral of dA, but what are our limits? We are going from 0 up to y. Now how do we define the limits? Why don't we take from 0 to b? Because look at the area that we have drawn. To sum up all of the areas, all of these small areas, you take one plus with another one, another one, another one, another one, another, and you see it just goes up and down like this. That's why we take from 0 all the way up to h here. This is h, all right? So that's how we define those limits. dA is what? dA here is equal to x times with dy. But x is equal to b, so dA is equal to b dy. Substitute it in, and we get A is equal to BH, which is the area of a rectangle. Now we find Q. So do we use QX or QY? Now we're looking for X. So that means we need to use QY. Again, QY is equal to integration of X curvy bar times with dA. X curvy bar is the middle of the area that we have drawn, which is b divided by 2. So substitute that in. And dA is from previous, which is b times dy. And then you work this out, you should get b squared h divided by 2. Okay, now we have QY and A. Just put them into the equation up here. You should get this, which is x bar equals to b divided by 2, which is visually, we can see that the middle of the rectangle is b divided by 2. So you might be thinking, why do I need to do all of these equations and integrations just to find something which I could find visually? Sometimes you may have a shape or a cross-section which is not so perfect, and you need to use integration or these first principles to find the centroid of that cross-section. Okay, now let's find y bar. Same, we draw the small red area vertically because it is the same as y, the direction of y. So y goes like this. So it's in the same direction like that. Now some of you have asked me, we can get the answer from this bar as well. We can get y bar when this area is drawn like this. Why do we need to draw the other one? Well, that's the basic principles. You need to do this to find x bar, you need to do this to find y bar. But it's also acceptable to derive x bar and y bar from just one area like this. That's also possible. I'm just teaching you the basic principles. So let's continue trying to find y bar. Again, we derive our limits here. Just visualize, put your pencil or paper or pen like this, and imagine we are trying to sum up all of these areas, and they go from 0 all the way to b. So that's why we have our limits from 0 to b. And we also get bh. In fact, you don't need to do this part because you can just take a from the previous part where the red bar was horizontal like this. But I'm just showing you the basic principles of defining a centroid. Now that we have q, we use qx or qy. Again, remember that y curvy bar will be opposite to q. So we want to find y, we have to use qx. Or another way of thinking about it is you want to find the direction, you want to find the centroid, but you want to find this value. It is the relation when we're talking about the definition. It is how this area relates to an axis. Which axis? This goes to the x-axis. So x-axis means we need to use qx. So that's the way of thinking about it. Then when we do this, you get h squared b over 2. Remember the limits. Now we put them into the equation here. We will get h over 2, which is visually, again, we know that for a rectangle, the centroid is going to be right in the middle here. So that's how we use first principles to derive the centroid. Now let's try another one. This time, this is for a triangle, not a rectangle, and we're only deriving y bar. Okay, so let's draw a bar, a red bar, a small area to find out our y bar. Remember, it's the same direction as y bar. So y bar goes up and down like that. So the small area will go up and down as well. The area dA is equal to y times dx. But what is y? In the previous example, where it's a rectangle, y is just h because it's a straight line. But now we have a slope here, so we need to use the line equation. Y equals to mx plus c. M is the gradient minus h over b. It's minus because it's going down, and h is the y-intercept, which is here. So you put that in there, and you put it back in here. So dA is equal to this. Now, let's find A, the total area. It's the integration from 0 to b. 0 to b. dA is this, so just put that in there, do the integration, substitute the values of b and 0, and you'll get A equal to BH over 2. And that's the area of a triangle. We have verified that we have found that the area of a triangle, a right angle triangle, is the base times height divided by 2. Now we find Q. Q what? Qx, because we're finding y bar, so they are opposite of each other. So Qx is equal to y curly bar times dA, but y curly bar is this, which is y divided by 2. But what is y? You need to substitute y, which is from previously, which is this whole thing here. So substitute it back in here, which is, don't forget to multiply by this one, okay? And it changes to dx. So it becomes y squared over 2. We substitute y in here, then we have to expand the equation. do the integration, substitute values of b and 0, and you should get h squared b divided by 6. Now try to do this step by step. Don't try not to skip any steps. If you're feeling that you don't get this answer, try to do the steps slowly and try not to skip too many parts. You will eventually get there. Then just plug values into this equation. You get h over 3. So that's y bar. Now I would encourage you to try to find x bar by yourself. And the answer should be b over 3. You can use the same bar like this, or you can make a new bar as well. Alright, now let's talk about composites. Composite means simpler shapes connected together to get a complex shape. When we break down the composite shape, we get simpler shapes. So to find the centroid of a composite shape, we just need to find the centroid of these simple shapes first. Imagine we have a T section here. We apply the same principles as before, this time using weight, and to find here the centroid of this T section is just the y curvy bar for number 1 times with its weight, and then we plus it with y curvy bar number 2 times its weight divided by the total weight of both. Then we get y bar. X bar should be the same, but we don't need to calculate because due to symmetry, x bar will be 0 because x bar will be in the middle. It's because it's symmetry. Left and right are the same. We can replace W with area, length, or volume depending on what we want to find or what shape we have, but usually we are dealing with areas because we're dealing with two-dimensional bodies, two-dimensional cross-sections. So area is the one that we're going to be using the most, and the formula is like this. It's quite similar. Just take the area of 1, multiply by its y, take the area of 2, multiply by its y, divided by the total area of both simple sections. Let's do example number 3. To find the coordinate of the centroid for this T-beam. Now this example has some numbers finally, so no more integrations are necessary. All you need to do is to multiply. So this is the simplified diagram. This number 2 and number 1, if you notice, they're both actually the same dimensions, they just rotated differently. This is 50, this is 50, and then this is 300, and then this is 300. So they're just the same shapes, just flipped differently. So let's apply the principle that we just learned. Area of 1 is 15,000 millimeters square. Area number 2 is the same. Y1 is from here all the way to the bottom axis. Okay, so it's half of this height, 2050 divided by 2, plus with the whole of this 300. That's why you get this. So we get 325. Now y2 is simply just 300 divided by 2 is 150. Plug all of these into the equation, you'll get y bar is equal to 273.5. So it's going to be somewhere in the middle there. Okay, quite simple. What about x bar? We don't need to do calculations because due to symmetry, x bar is 0. X bar is right in the middle here. Okay, so that's it for lecture number 11 about centroids and center of gravity. So just break down complex shapes into simpler shapes, find the centroid for those simpler shapes, and then just apply this formula here, or let me give you the base formula there, here. Just apply this one, you should be fine. It's going to be easy to find the centroid and center of gravity of complex shapes. Okay, so next we're going to be learning about moment of inertia. And I like this quote from Dr. Seuss, is that the more you read, the more things you will know. The more that you learn, the more places you will go. So try to read a lot. Doesn't really matter what you read, but try to read some books, magazines, articles. Just read, but don't try not to stuff too much junk. All right. So see you in the next video.